Oh, this is wrong. That's the one I wish I was giving. Never mind.
It's a new dog.
It's yeah. This is bon. The previous one was Ruby. Ruby. This one's bonsai.
There's not a sandwich again.
So we're staying off the reservation here a bit, but I think again this might be well. This I'm going to talk quickly about the thick disk. Just some new results in there that mainly because I think it's an. I guess the relevance here is that the new results show what you can do when you have lots and lots of data points, which is what we'll have with Gaia. And it does actually show, it gives the answer of why fitting two straight lines is always just the first approximation, and it always turns out to be different when you look at things in more detail. The other thing I'm going to talk about is the age metallicity distribution in the disk, and a bit about measuring stellar ages. And this is relevant to the final talk I'm going to give tomorrow, talking about the sun, because part of the rationale, you remember, for having the sun move was that it didn't fit the local metallicity distribution at a given age was large. And the main thing to take out of this is that the older a star is in the field, the more difficult it is to measure its age. Okay, so the thick disk. This is the plot I showed before. Distance above the plane, density, stellar density, and the run one exponential, two exponentials. And then there is clear evidence that you can't just represent the density distribution vertical to the plane of disk stars with a single exponential. And this plot over here, this is from Urich et al. Analysis of STSS data, much larger sample, much higher precision photometry. And again, they fit this with a combination of density laws, but particularly splitting it into two populations. So the properties that have been ascribed to the thick disk, it's an old population. You can tell that simply by looking at large distances above the plane, and you see very few OBA stars. The turnoff is round about G. It's not as old as the halo, perhaps, but it's still a pretty old population. To get stars up there, you need significant velocity dispersions, and various authors, various researchers have tried to estimate the velocity dispersion for this population. The numbers I give here are velocity dispersion of 35 kilometers per second vertically is from Kiba and Beers. The rotational lag is generally given as 30 to 60 kilometers per second relative to the rotational velocity of the sun. And the abundance distributions are generally characterized as mildly metal poor, average metallicity minus a half, but with a big tail extending to lower abundances. And the big problem in quantifying this is that it has been consistently difficult to identify a nice set of criteria that would split off the thin disk from the thick disk. The one thing that did come up in the late 90s, about 10 years ago, Fuhrman particularly led this charge, but Bensby and various other groups have looked at this, and it turns out that stars that you would identify as thick disk stars, these are stars that have substantial lag in velocity relative to the sun. This is metallicity, and this is it's a Bottlinger diagram. So it's the square root of the velocity squared. So it's basically total velocity versus metallicity. These objects in here, the kind of light circles, are identified as thick disk stars because they are higher velocity than the typical disk stars. And it turns out that they are also alpha enhanced, suggesting that they formed early on in the galaxy's history, again, before type 1a supernovae could come along. So that to me was the first real clear signature that this thick disk population wasn't just a thin disk, a set of average thin disk stars that were being scattered up to large distances above the plane. But that's actually the problem, that how do you manage to create this population with this large velocity distribution perpendicular to the plane? How do you, as I mentioned, talking about the kinematics, the standard scattering processes, they do a pretty good job getting up to about 30 kilometers per second, maximum, or 25 to 30 kilometers per second in W, just with scattering off molecular clouds. But then things tend to flatten out because the star is spending less time on the disk, it's less subject to scattering. So actually cranking up the velocity dispersion much beyond that is difficult to do at the sun's location in the galaxy. So there were two main hypotheses that we put forward to try and explain the thick disk. Either it formed when the disk was thicker. I've said, well, it's still collapsing, but it may just have been that the disk was thicker, so you form them out there, and somehow the disk settles afterwards. Or you manage to excite the disk by inputting energy, and the obvious way of doing that is a merger. So I'm just going to run through quickly a bunch of models that have been proposed for explaining the thick disk. And Villalobos and Helmy, this is in the context of the satellite accretion model, the Via Lactea simulation, the dark matter, where you accrete a number of smaller satellite galaxies. And provided the mergers can total about 10 to 20% the mass of the host galaxy, you can puff up the disk. These models here basically are just showing a merger process going on, an n-body simulation, and basically you end up, whether it's retrograde or prograde, you can puff up the disk and get velocity dispersions that are in the ballpark of what we're being ascribed to the thick disk. Another way of doing it, actually I got that wrong. This is merging satellites. This is the one that Abadi et al. Are taking the lambda CDM. And in this case, it's not visible here. Basically all of these, you end up with a kind of thickened disk. In this case, it's actually the satellites that make up the thick disk. So they're talking about there that the puffed up population is coming from the accreted satellite galaxies. In this model here, you accrete a mass and it puffs up the stars that are there. So you get a mix of the disk, the disk population that was there beforehand plus the satellite. Here it's the satellite that's contributing to the thick disk. And the way that you do this is a plot of the age of the population against the star formation rate. And there are various spikes in here, which are where a satellite gets accreted. And it not only puffs up the disk, it also has a spike in the star formation. Gas-rich mergers. That's another thing that's been talked about. In this case, you have a gas, you have I guess a dwarf spiral, a dwarf irregular galaxy that has a lot of gas with it. And you actually form stars in situ at large distances within the disk as you accrete it, as you shock the gas and form stars. And again, through that model, this is the density law, you can actually come up with something that matches the density distribution. So there are multiple ways of trying to form this population. And the most recent method that's been proposed is our friend radial migration. In that case, the argument is that as you go closer into the center of the galaxy, the disk is going to get thicker because of a larger mass density in there. So dynamically, you expect to have a higher velocity dispersion. If you can take these inner satellites, take these stars from the inner disk and migrate them to the outer disk, then you can bring in this thickened component locally. But these stars locally were actually born in a different part of the disk. And this diagram here is basically just showing the probability, given that something started at 5 kiloparsecs. Yeah, 5 kiloparsecs for this one. It can end up anywhere between 0 and 10 kiloparsecs. And in this case, it's 7.5 kiloparsecs. Again, you spread things out. So you can bring things from the inner disk out. And if they have a larger velocity dispersion, you can build up the profile here. And everybody can produce this plot. The density law perpendicular to the disk, you can basically explain the thick disk. Okay. So those were the models that were in play. And recently, there's a nice series of papers by Bovie and collaborators. I think it's Bovie, Hans-Walter Rix, David Hogg, and a few other people from the STSS and STScI collaborations. And here's the advantage of an enormous data set. They're analyzing spectroscopic data from STScI, which is one of the follow-up surveys to STSS. They have 30,000 G stars. They can get abundances and velocities from the spectra. They get distances from the photometry. And what they've been able to, these diagrams down here, this shows the alpha abundance to FE, alpha to FE distribution in terms of the raw, the sample. They've corrected for that based on their selection effects. So this is actually the distribution in terms of the galactic populations. But what they've been able to do with this large sample is to slice things up into small subsets based not only on the FEH abundance but also on the alpha abundance. And essentially what they find is it's not two populations. There's a continuum in there. So this lovely multicolor plot is, this is Fe over H against alpha abundance. So these are alpha enhanced up here. And the color refers to the velocity dispersion, where blue is low velocity dispersion and red is high velocity dispersion. Then here, this is looking at the, it's the gradient, basically, in the velocity as a function of height above the plane, where green is zero gradient, and blue is large negative, red is large positive. So this is looking at, so when you measure, they can also slice things up in terms of height above the plane. So they can look not just at the velocity dispersion as the population as a whole, but going up there. And essentially what they find is that when you slice things up by metallicity, and these plots here are now height above the plane against velocity dispersion, with blue for, this is in terms of alpha enhancement. So low alpha enhancement to high alpha enhancement, or if you like, low metallicity to high metallicity. No, high metallicity to low metallicity, because the high metallicity ones have the low alpha enhancement. Essentially, you have a whole series of isothermal populations in there. But when you slice things up into these small bins, it looks like a continuum. The stars down here have a low velocity dispersion. The stars up here, which are up there, have a high velocity dispersion, and that velocity dispersion doesn't change as a function of height above the plane. So it's basically a continuum. It's a smooth distribution. There isn't one group of stars that are thick disk, another group of stars that are thin disk. It's continuous throughout there. I think I've said all that. The other interesting thing is they can look at the radial density distribution, and they find that the lower abundance populations are actually more centrally concentrated in the galaxy. Yeah?
So, perhaps a very naive question, but how, which degrading mask could you put on top of this to revert it back to the original detection of the thick disk? I mean, how can you degrade this data to get reality out?
By, you would have to multiply it by the number of stars in each population. Yes. That's basically what you're doing. So, I mean, essentially, the continuous distribution in density reflects the fact that you're putting together, there's a continuous distribution in density here too. I think that's actually what was shown here. So you would actually want to take this distribution here. This is the true number of stars. Dense means there's lots, low density. So you multiply that against, I guess, this, and you should get the number distribution as a function of height above the plane. So so you're taking two continuous distributions, and it just so happens to give something that can be fitted by two exponentials. So I think it's a nice result. What does it mean by their isothermal? To me, this suggests that the stars are well mixed. I'd actually be interested in what you think an isothermal population means. But to me, it suggests that they're relaxed, they're in equilibrium with the galactic potential. That they've essentially lost all trace of their formation. Okay. So this, I think I've sort of said this, but so the stars that have called the thick disk are just the oldest, most metal-poor stars in the disk. There's a continuum of properties, and previous surveys found different, so when I say previous surveys found different results with regard to detailed properties of the thick disk because they were taking different subsets from this continuum. If you take metallicity as a proxy for age, the oldest disk stars formed in a more centrally concentrated distribution, and that does tend to fit with models for building galaxies from the inside out. Yeah, so the higher velocity dispersion at lower metallicity, and this then would then tie in with the Schoenrich and Binney radial migration concept. If you've got a higher velocity dispersion in the center, you've got this puffed up disk in the center that's coming out here, that's adding out here. Right, and so I think this may be a big step forward in terms of understanding the disk properties within our galaxy. And a take-home message, if you've got a lot of data points and you analyze them correctly, you can actually get some really interesting stuff. And that's what Gaia is going to do. So, and as I say here, even although we now might understand more about the disk, I'm still not entirely sure we understand why it looks the way it does. But I think we've got to, if you have a clearer picture of what's there, you can actually try and interpret it better. But anyway, this is even less relevant to this course than the rest, but I still think it's an interesting result. Okay, so moving on to something that we might care about. This is the age metallicity relation. So I mentioned this before. This is the Edwards and et al. Plot of age against metallicity for stars near the sun. This is a plot of, these are actually OB stars. This is the metallicity gradient going from 0 to 20 kiloparsecs within the galaxy. The sun here actually sits below the mean line there, but which is not unexpected since these are stars, OB stars, these are stars forming now. So the argument is, the question is, why do you find such a large dispersion in metallicity here when there's a somewhat smaller dispersion in metallicity forming at one place at any one time? And what I'm going to talk about here is more about how you're actually computing this age metallicity relation, because it rests on two quantities: stellar abundances, which we can actually measure pretty well now. It's hard, but we can measure them pretty well. And then stellar ages, where it's really depressing, frankly. So if you've got a nice intermediate age, gas-depleted star cluster, and they're all in the same place, you can just put them down in a color magnitude diagram and fit an isochrone and get a reasonable age estimate. If you have a young cluster, then you can do the same exercise, but there are caveats. There's reddening by local stuff. There's reddening by circumstellar material. There's emission from circumstellar material, from accreting material around the stars. There are binaries. We know now there are binaries. They can really make things difficult. There might be a real dispersion in ages. And then once you've done all those measurements, you're faced with the fact that the pre-main sequence isochrons are much more difficult to calculate generally than evolved stars. So there's a whole lot of uncertainties going in there, but you can still get some kind of age out of it. And again, this is Lynn Hillenbrand's Orion Nebula cluster diagram. So there are various techniques that have been devised for trying to measure the ages of individual stars in the field. And that's the thing, you're trying to measure the age for a star that's sitting out there way after it's left its cluster. It doesn't have friends that you can put in a color magnitude diagram. You can actually put the star itself onto a color magnitude, against an isochrone if you know its distance, which means you know its luminosity, its effective temperature, and its abundance. You can carry out that exercise. But it's always more reassuring if you have friends to tell you you're measuring the right thing. Rotation has been used as an age estimate for stars. The argument there is that stars start off with a lot of angular momentum, they gradually lose it. The mechanism that's usually discussed is magnetic braking. So essentially the magnetic field within the star tries to get the surrounding corona of the stellar wind to rotate with the star at co-rotation rate. So you lose energy there. Rotation is also tied into activity, chromospheric and coronal activity. In Down to the mid-Ms, that's a rotational dynamo effect, where you have a radiative core and a convective envelope, and it's the boundary between the two that drives the magnetic field. On the other hand, when you get to fully convective M dwarfs, they don't seem to care that they don't have a radiative core, and they're just as active. So maybe it's supposed to be a shear mechanism for magnetic field that's going on. Astroseismology. I'll talk more about that actually tomorrow, but here basically what you're doing is you are looking at the pulsations of the star, you're using that to estimate the sound speed or you're using that to constrain the sound speed within the star, and the sound speed within the star depends upon the mean molecular weight. The mean molecular weight depends on how much helium you have. So the older the star, the more the helium, the higher the mean molecular weight, and the pulsations change in a way that somebody who works in helioseismology and astroseismology can interpret. And I just give you that formula. So rotation. There's been a lot of work on this in recent years. It wasn't 9207. I should need to change that bracket. But this is color, and these are data for stars in open clusters, for a range of open cluster stars. This is basically the period relative the normalized period. And what you can see if you squint is that there is for a given cluster, there does tend to be a broad relation traced out by the stars in that cluster. There are a whole bunch of stars, if you're just looking at the red circles, there's a whole bunch of stars that fall below that relation. The argument there is that, well, the only reason that they fall below is because you're seeing a projected rotation. So, but this is a messy diagram. And I guess Dave Soderblom's review article does a really good job of going through all these methods. One of the things that he points out is that this is taking the rotation period here. It's scaled relative to the solar rotation period, but it's rotation period as measured for stars in NGC 2264, M50, M34, and the Hyades. And what you can see is that there's a big scatter in there in terms of the measured rotation period. This is against V minus I, so against temperature. But there's a big scatter in terms of the properties. On the whole, as you go from younger clusters to older clusters, the rotation and velocity comes down. But there's a whole bunch of caveats in using this in the field. You need to get spectra. And even you can, for young objects, you can measure rotation period based on their photometric variability. But even once and in that case, you can actually get the real rotation period. For spectra, you're measuring a line broadening, so you're measuring the projected rotation, which, as I say, may account for some of the scatter there. The other problem is that rotation loses sensitivity with age. For the Hyades stars, you've got this nice tight relation, but what that is basically saying is that they've slowed down a lot. There isn't a big space in here for going to slower rotation, and nobody's actually calibrated rotation as a function of age for older clusters. And as I say, there's probably a lot of intrinsic scatter. Activity. So I mentioned this before. This is in solar to F to mid-M type stars, you've got this alpha omega dynamo where the shear between the radiative core and the convective envelope, and that drives the magnetic field. And the magnetic field then leads to activity on the surface, both chromospheric activity and then coronal activity. It's essentially the same thing we see in the sun with spots and prominences, although we're fortunate enough that the sun is a remarkably quiet star. The other complication in here, on the whole, so the level of activity in a star is tied to the rotation rate. It's this shear property going in there. So the faster the star is rotating, the higher the level of activity. If you have a close binary, you can keep a star rotating actively for many years, many years more than you would normally. You can measure chromospheric activity relatively straightforward. Calcium emission in solar type stars, X-rays, H-alpha emission in M dwarfs. But again, it's not a nice clean relation. This complicated diagram is the fraction of the flux output in H-alpha for M dwarfs, or going from K through to M9. And there's a bunch of different, or data for a bunch of stars from different clusters on there. The T-Hydra Association, which is about 10 to 20 million years old. The Hyades, which are the blue dots. The Pleiades, which you probably can't see, but there's a whole bunch of cyan triangles in there. And then for the field, the green background. And the main thing that one can take away from this is that there's a big range in activity even for stars of the same age. The Hyades stars really show a very large dispersion. Same thing in X-rays, another multicolor plot. In this case, the yellow are the Pleiades stars. And you can see that even though the Pleiades stars are all the same age, there's a big range in coronal activity. And that's only at an age of what? 120 million years? Good. In fact, it actually gets quite entertaining because I think Mark Giampapa did this. It's not just that stars have activity that changes in long secular timescales. We know from the sun that there are shorter period variations. We're just entering solar maximum. What Mark Giampapa did was to take M67, data for activity for stars in M67, plot that up as a histogram here. And then he said, what happens if I take the sun and I measure its activity from solar minimum to solar maximum? How does that match up with M67? And the answer is that solar minimum to solar maximum actually spans a large chunk of the range of activity in M67. If you were to plug that into the standard formula that people use to estimate ages based on chromospheric activity, you would estimate that actually, I guess I turned that the wrong way around. If you were to take the standard formula for estimating age based on chromospheric activity and then take the M67 stars, which we know are all the same age, you get an age range of 1 to 7 billion years. So chromospheric activity it's certainly not a precise age estimator.
But it's accurate.
It's very accurate. It can be accurately really, no, well, actually, no, it's precise. It's not accurate. It's
accurate, but not precise.
It's both. You can find really young. The other way of doing things then is to look at isochrone fitting. And this is just the standard technique where you will take a theoretical isochrone. If you know the accurate parameters for a star, you can put that star down on this diagram and try and figure out what its age is. And again, the main point here, the older you get, the slower stars evolve, so the less accurate your measurement will be. So measuring abundances, there are a variety of techniques that we use for that now. Photometric measurements, I mentioned ultraviolet excess, delta U minus B. Generally, those are measuring line blanketing. This is the other half then of the age metallicity relation. Stromgren indices are one thing that I'll mention. Spectroscopic analysis, you're looking at much more detailed data, you can get much more accurate measurements. So this is the best way, I think, of measuring abundances. High-resolution spectroscopy. The advantage is that you can do a line-by-line analysis. You can do spectral synthesis, fitting everything at the same time. The disadvantage is that getting these data is hard. You need to have a big telescope. You need to have a lot of time to do a lot of stars. That's the main reason I think that people will largely move to photometric techniques. Photometric techniques you can apply across the board. The problem is that you have to recognize that with a photometer, you are simplifying things. These are the Stromgren bands, U, V, B, Y. This is a spectrum of a G star going from 3,000 to 6,000 angstroms. The U is measuring blanketing. U index is measuring the flux here, measuring blanketing at the ultraviolet wavelengths. V is close to H delta. B is measuring a continuum feature here, and Y is essentially measuring the 5500 flux. And the standard Stromgren metallicity index is basically looking at the relative blanketing. I think it's U minus V minus B minus Y. Is looking at the blanketing in the ultraviolet part of there. But you have to recognize that this is really a big bucket method of measuring things, but you can do it for a lot of objects. Actually, V minus B minus B minus 1. So let me move on past that. So the age-metallicity relation for the disk. This is the classic work by Bruce Twarog, which was looking at UVBY data, Stromgren data, and Isothermal fitting for F-type stars. And he came up with a fairly steep relation between, this is age going from 0 to 12 billion years, and metallicity from solar metallicity, the sun's here, down to -1. And he found from his data a quite steep relation between age and metallicity. Since then, there have been more investigations. And I'm going to talk about one in particular here that I looked at, which was taking, I didn't actually do any of the analysis of this data myself, but I took the results from some work that Jeff Valenti and Deborah Fisher did, analyzing data from the Cank Survey for planetary companions. That survey covers 1,000 sun-like stars. It basically covers the stars that the Geneva sample doesn't cover. They published their data, all of it. It would be nice to see the rest of the sky. But they surveyed essentially solar-type stars. So this is color magnitude diagram, B minus V 0.8 to 0.4, a few subgiants in there. It's largely a magnitude-limited sample. There are some people who, because there was a big emphasis on finding planets around metal-rich stars, there are some people who think that they actually pre-selected the stars based on metallicity, and that's not the case. It was actually a magnitude-limited sample largely. All of these stars, almost all of them anyway, have accurate metallicities and astrometry with Hipparchus. So you can take that sample and get a reliable get a volume-limited sample. Essentially, they observed about half of the Hipparchus stars within 40 parsecs of the sun. Yes, I guess I said that before. And this is the age-metallicity relation that they derived. This is from isochrone fitting. And to be completely honest, they derive a probability distribution for the age for each star in their sample. And these error bars up here, this is the age-metallicity relationship based on their data. These error bars there are the uncertainties in their ages. They actually, if you plot up those data against metallicity, you get something that's actually pretty close in slope to the original Twarog relation. It doesn't show the nearly as big scatter as the Edwardson sample. That's the Edwardson sample plotted here. There's actually some data from activity. And then this is the most recent analysis based on Nordstrom et al. Analyzed something like 40,000 G-stars from the Geneva-Copenhagen survey. They find absolutely no correlation whatsoever between age and metallicity. Even less of a correlation than Edwardson found. And that's, their data has been reanalyzed recently by Luca Casagrande and collaborators. And his data are plotted here. So this is age metallicity from Luca's reanalysis. This is mass against metallicity. And something that may not be clear here, but the interesting thing that I'm seeing is that they seem to find they find an upper envelope which decreases in metallicity going from high mass stars to low mass stars, which I find slightly worrying. All of these metallicities are based on Stromgren photometry, and the ages are based on main sequence fitting, but using the Stromgren data to give the metallicities. And again, they find this banana-shaped feature here. This is what you get from the Keck sample. There's an awful lot of scatter here. The ages are uncertain, but you actually get more of a trend with age against metallicity than you see in this sample here. And again, this is factoring into what we're thinking about tomorrow, is what's the justification for saying that the sun actually changed its location in the galaxy. Because if you plot up the age-metallicity relation here and put the sun in it, the sun actually sits in the right place. You know, the sun is at solar metallicity. The average metallicity, the sun is at solar metallicity. And it's right. The average metallicity at an age of 5 billion years is solar, according to that relation there. So, age distributions, let me skip over that now. These are not really terribly relevant. So, thick disk, I think we've made big progress there. Field star ages, like I say, just be thankful you work in clusters. But it's possible the age metallicity relation may have less scatter than previously thought, and that could factor into whether we think the sun moved or not. And that's it. Thank you. Whoever made up this schedule with me having 4 lectures at the end really deserves. Carry on, Mike.
I remember after the Hipparchus stuff was done, more or less, people were trying to fit the star formation history of the
Right. Actually, that's what I leapt over. This might be what you're thinking of. Hernandez, Valls-Gabo, and Gilmore. They took, and I guess James Binney, I forget, they did the same exercise. This is what this is taking the color magnitude diagram and essentially doing a point-by-point fit to ages and then putting down the ages in a plot here. And they came up, Hernandez et al. Came up with this remarkably spiky relation, which I would say is basically consistent with a flat line. That they say that there were gaps in the star formation rate 2, 6, 10 billion years ago. I don't think that we actually can estimate ages to anything like that accuracy. And what I skipped over and I didn't show is that everything, if you try and look at the age distribution within the galactic disk, the best fit is a continuous star formation rate. There's no indication of a giant burst of star formation at any particular epoch.
Has anyone, I guess naively looking at the star formation history of the universe, I wondered always why people didn't see it rising. Do you think that could be observational or just impossible to see?
I think I can't call to mind anybody who's argued for a substantial burst in star formation. But the other thing to remember is that the star formation rate for the things like the Maddow plot are plotted against redshift, which is very nonlinear with time. So if you make it more linear with time, then maybe there's not the same burst of star formation early. But I was thinking about that might go the wrong way. But
other than this is the disk, so it must have been in a sort of gas dissipative state at early times.
right, that's
Whereas
yeah.
most of the star formation in the Milky Way was in the bulge at high redshift. So I suppose the bulge has a peak in old ages. So I guess if you add them together, it kind of fits your remark.
Yeah, that's true. This is looking at local stars. So even with migration, you're probably only going in to, 4 or 5 kiloparsecs out. You're not sampling. If you're looking at remembering that half the age, the redshift 1 was half the age of the universe.
I guess I'm thinking a little bit of the Sloan stuff where we are eating dwarfs over time and those things have star formation histories themselves.
But they're not dominant.
Right.
Disk.
We're only taking small snacks. So,
So there's
Kathy?
something about the alpha-over-ion relationship, which tells you that we haven't had lots of bursts in the star formation history of the Milky Way.
I mean, I think alpha to iron is only telling you about the initial stages of star formation. I mean, how would it tell you about bursts? Because
I'm vaguely remembering work by Rosie Wise and Jerry Gilmore. I thought the idea was that if you had a big burst of star formation later on in history, at more recent times, then you'd suddenly get a rise of alpha over iron because you'd be producing ejecta,
right.
you'd be producing oxygen relative to the iron that was seeping out on a time lag from the type 1 supernova.
I mean, I guess that's probably true that if you had a really big burst, you could get a kind of two-step alpha.
They could employ star formation histories and concluded that it had to be pretty flat, but how
Hmm.
you know, the scale of our discussion, I'm not sure, but I think that's got some diagnostic power relationship from my memory.
Since Jerry was involved, I should answer. Any more? Chris? Nope. Well, thank you. And I promise we'll talk about associations tomorrow.